going to give you a problem. I'm going to give you a problem. Start with that.
So we've been doing a lot of work to use visual patterns to develop an understanding of algebraic concepts with students. And one way that we do that is through a very scaffolded approach. We modeled that with the arch problem. But another way, a very rich activity that you can do with visual patterns is an open approach, what I would categorize as a problem-posing approach.
Just looking at this quickly, you'll notice that it's very different from the arch problem. Okay, and we'll talk about that later. But I just want to say there are two questions on this page. What's question number 1 say? What do you see? And what's question number 2?
The scaffolded is more about starting with something concrete and building towards something abstract. But with the open approach, and there's a lot of things that are really going on. For one, it's just about helping students see that just from making observations, you can pose and get to you can get to real math.
This activity is doing two things. It's modeling, even if you're not sure yet how it connects to this, how to do some pretty complicated algebraic stuff. But it also is showing a different way to kind of use these kind of problems and these kind of activities with students.
We call it Visual Pattern 141 because it's from a website called visualpatterns.org, which is a great resource. It's really the model that we're showing, and it would fit with any of the patterns on that site. So I'm going to use pattern 141 as an example. So there's 4 stages of a pattern. You can see that it's growing from stage to stage as it's changing, but there's no definitive answer. There's not one way to look at it. We encourage that with the 2 prompts that go along with the pattern when we give them to students or teachers or anyone who's doing this activity, which is, what do you see? And just pose some questions, pose some problems that you're thinking about as you look at it.
What would be the number of completed squares in the 20th stage?
Wait, completing what square?
Not completing the squares.
Well, completing the missing part.
Stage.
Right.
So, I mean, the question I asked.
So what you're saying is that he allowed you to see this exchange in a different way than you had seen it before.
Right.
So how is it that you saw anything? What did you?
I saw it as 2 different levels. So I was trying to figure out the relationship between this level and this level, 6 and 2, just with the squares, and they...
Students write questions to their own level, but also their interests. One totally legitimate question to this is, what would the next figure look like? Right? Which maybe isn't as complicated as, what's the relationship between the changing perimeter and the area of these shapes? Or if you created these figures with toothpicks, how many toothpicks would that take?
Other strip? 3, 2, 1 and 3/4.
So students, they put up all the questions on the wall, and everybody takes a look at them, and then they get to choose, and they get to work in their pairs. And there's lots of different ways, of course, to handle this. One way that I really like is to have groups who are working on a particular question write their question on the top of a big piece of paper, newsprint. So as a group, we're working on some real mathematics that came out of our own curiosity, and we're going to be presenting what did we get out of this process to our peers.
And from that pattern, we made a way to find the area, no matter what the stage number is. We can build the area formula for this shape and for this pattern in many different ways. There's not just one way to do it. There's lots of ways to do it, but all of them should come out to an equivalent algebraic expression. So if we evaluate these, or simplify these, that is, all 4 of them will come out to the same thing, which is area equals 2 times n plus 1 squared.
I love to have students put those up on the wall, and then they mill about, and then give them post-its, and they annotate. They write what they appreciated, what they liked about a finding, and also what questions they have. They're mathematicians, and they're sharing their work with their peers. This is how I think of it.
And then we got upset because we were looking at someone else's formulas, which worked for everything, but one of their formulas didn't work for this. And so we were arguing over which.
Did you resolve that?
I think we both agree it should look like this. What we don't know is why that formula won't work. He had like 4 different formulas for 4 different parameters of the shape, and why the fourth formula works for every stage except 0. And the only thing I can think of is that 4th one was about the wing, and there is no wing. So the pattern can't apply. So 0 is a weirdo.
So in addition to the way that students kind of pick their own level, they're also just the benefit of seeing the sheer number of questions that you can ask and the sheer number of ways that you can answer those questions, I think is a real impact in what mathematics is to them. In addition to being this opportunity to explore some pretty intimidating levels of mathematics. It really frees students up. You don't have to look at this change algebraically, you can look at it geometrically, and you can look at it to wherever you're, in whatever ways you're able to look at it. Problem posing, that's real world math, because part of the way you do math in the real world is you have to create a problem. I think it also really gives students ownership over the problem, because they are setting the math work that they are doing for the day. They are really determining the direction that it takes. They're asking the question that begins the journey.